Let's start with a simple question. What exactly is service discovery? In a modern environment, you aren't just running one instance of an application, you're running dozens. They might be on different bare metal servers, different VMs, or scattered across containers on the same host. Imagine App A needs to send a request to App B. The old school way was to manually hard-code App B's IP addresses into App A's configuration, from which it could then pick one and send the request. But what happens when you upgrade? Or what if you scale up to handle more traffic? New versions might spin up on different VMs or containers with fresh IP addresses. If App A is still using the original addresses, it has no way to reach the new instances, leaving them untouched and effectively useless. A simple fix is DNS, a classic service discovery mechanism. When you update your app, you update your DNS records. It works, mostly, but DNS has two major flaws. To avoid overwhelming DNS servers, clients cache IP addresses locally. If you're rapidly cycling through VMs or containers, your client might keep trying to talk to a ghost instance that has already been terminated. The more serious problem is that DNS has no idea whether your app is actually healthy. If an instance crashes or hangs, DNS will still happily resolve to that broken replica, leading to failed requests and a poor user experience. This is where Kubernetes changes the game. When you deploy App B in Kubernetes, you use a deployment object, let's say with 3 replicas. Kubernetes uses a reconciliation loop to ensure those 3 instances are always running, no matter what. In Kubernetes, we call them pods, but pods are ephemeral. They live, they die, and they get replaced, each time getting a new IP. To solve this, we use a Kubernetes service. This gives you a stable virtual IP and a DNS name. Unlike traditional DNS, the Kubernetes service DNS resolves to that stable virtual IP, which means zero caching issues on the client side. When pods come and go, kubeproxy updates the backends almost instantly, unless you use a headless service, which we'll cover later. Here's the clever part. In Kubernetes, deployments and services are completely decoupled. They connect using labels. When you create a deployment, you tag your pods, for example with App B label. The service then uses a label selector to constantly watch for any pod with that tag. Because of this layer of abstraction, we can do so much more. For example, we can check the health of each instance via readiness probes before adding it to the service, so requests are always forwarded only to healthy instances. And of course, you get load balancing right out of the box. Requests to the Kubernetes service are distributed using a random or round-robin algorithm across healthy pods for even load distribution. App A could be in the same cluster, using service DNS directly, or external, via node port, load balancer, ingress, or gateway API. Knowing the differences between ingress and the gateway API is actually a very common interview question. I just released a deep dive video explaining different ways to expose your application, so if you're preparing for interviews, you'll definitely want to check it out next. Kubernetes also simplifies application upgrades by removing the need to manually compile binaries or to manually distribute files across multiple virtual machines. Instead, the process is automated and safe. When you build a new Docker image, all you need to do is update your deployment. By default, Kubernetes uses a rolling update strategy. It starts by creating a new pod. Once that pod is healthy and the readiness probe passes, Kubernetes terminates an old one. This step-by-step verification ensures your application stays online during the transition. If something goes wrong, you can quickly roll back to a previous version with a single command. A typical CI/CD pipeline works like this. First, a developer pushes code to a remote repository. A CI tool like GitHub Actions triggers unit tests and creates a new Git tag. This tag is then used to build and push a fresh Docker image. This ensures that the version running in your cluster perfectly matches a specific commit in your source code. Next, Argo CD, running inside Kubernetes, constantly monitors your Docker image repository. When it detects a new version, it updates the Kubernetes manifest and synchronizes the cluster state. This triggers that same safe rolling upgrade automatically. For development environments, we usually deploy every new version continuously. For production, we take a more controlled approach. Once a week, a script creates a pull request to sync all stable versions from development into production. Once merged, the production apps are upgraded. For even more control, the new Gateway API allows for canary deployments out of the box. You can shift just 5 or 10% of traffic to the new version, monitor performance, and then slowly scale up. From automatic rollouts to fine-grained traffic shifting, Kubernetes gives you a variety of built-in options for safe, reliable deployments. In Kubernetes, containers are ephemeral. If they save data to a local file system, that data disappears the moment the container restarts. To solve this, Kubernetes uses a storage orchestration mechanism. It ensures data survives pod restarts and follows a pod if it moves to a different node. This abstracts away the complexity of providers like AWS EBS, Google Persistent Disk, or NFS, allowing developers to request storage without worrying about the underlying hardware. There are three main components you need to know. First is the storage class. Think of this as a blueprint. It defines different tiers of storage, like fast SSD versus slow HDD, and allows Kubernetes to provision volumes automatically. Next is the persistent volume, or PV. This is a piece of storage in the cluster provisioned by an admin or dynamically by a storage class. It's a resource, just like a node is a resource. Finally, there's the persistent volume claim, or PVC. This is a user's request for storage. Just as a pod consumes node resources, a PVC consumes PV resources. It defines the specific size and access modes required. To deploy stateful applications, we typically use a stateful set. Inside the stateful set, you define volume claim templates. Based on this spec, every pod created by the stateful set gets its own unique PVC, which is bound to its own PV. If you run 3 replicas, you get 3 distinct volumes. The best part? If a pod is rescheduled, perhaps during a node upgrade, the volume automatically detaches from the old node and attaches to the new one where the pod is running.